This is the instructional video for assignment number 141, pH practice problems. So for question number 1, you have to calculate the hydrogen ion molarity given this information. And hydrogen ion concentration can be determined by using this formula, 10 raised to the negative pH. And the pH of this solution is given as 3.0, so we can plug into the formula, 10 raised to the negative third power. We can rewrite this as 0.001 molar. And since we're looking for the hydrogen ion concentration, you should label it with the proper unit and what this is. So this is the answer for question number 1. For question number 2, it says provide the numerical calculations to demonstrate that the percent dissociation of the weak acid is 2%. Now, percent dissociation can be determined by taking the ratio between the concentration of dissociated hydrogen ions over the concentration of the acid, the associated acid. Now, we already calculated the concentration of hydrogen ions from above, from question number 1, which is 0.001. Now we have to find the molarity of the acid, and we can find this by taking the ratio of number of moles divided by the volume. You can actually do it in 2 different ways, but we can actually set up a proportion to calculate this value also. Let's go ahead and do that. So we know that there are 4.95 times 10 to the negative 3 moles of acid contained in 100 milliliters of solutions. And remember, molarity is defined as how many moles of the substance is contained in 1 liter or 1,000 milliliter of the substance. So when you solve for x, you get 0.0495 molar of acetic acid solution. Now we have to plug in this value in the denominator because that represents the concentration of the weak acid that we have, 0.0495. And when you take the ratio between these two numbers, 0.001 divided by 0.0495, you get 0.02, which is the same thing as 2.0%. You move the decimal twice to the right to go from decimal to percent. So we in fact have demonstrated that percent dissociation of the weak acid is equal to 2%. So for question number 3, now we have to calculate the volume of 0.225 molar sodium hydroxide solution that's required to completely titrate or neutralize the acetic acid in the original solution. Now this is very similar to what we did in last week's lab, good titrations. And remember, titration can be thought of as a battle between acids and bases. One base kills one acid. So that means at end point of your titration or neutralization reaction, number of moles of acid will be equal to number of moles of base. Now, we know from above that we started with these many moles of acetic acid. So moles of acid is equal to 4.95 times 10 to the negative 3 moles of acetic acid. Now at end point, we're going to have equal number of moles of base. So that means we're going to have 4.95 times 10 to the negative 3 moles of sodium hydroxide. Now, we already know how many moles of base, sodium hydroxide, we need at our end point of titration. And we know the concentration of sodium hydroxide solution that we're using. So this is a one-step conversion that we have to do. so that we can calculate the volume of this solution that we need. So let's go ahead and start with a known number, 4.95 times 10 to the negative 3 moles of sodium hydroxide. And now this is a conversion factor. This means that there are 0.225 moles of sodium hydroxide contained per liter of solution. So I'm going to put moles on the bottom, 225 moles of sodium hydroxide contained per 1 liter of solution. That's the definition of molarity. And now when I multiply these two numbers, moles cancel out. So I can just type this as 4.95 times 10 to the negative 3 divided by 0.225. So I get 0.022 liters, which is the same thing as just 22 milliliters. That's the answer for number 3.